Okay, so we're going to continue by warming up with sequences. Can you guys remind me, what are the three notations we express sequences with? I heard list. Oh, it's so hard to get to this over here. Let's see. So I heard list. Oh man. I have a feeling I'm going to have to just retape this later, but that's okay. What else? Explicit. Working with that a bunch. And the one we haven't worked with too much yet, at least, is recursive. Okay, so we're taking these lists and we're supposed to make them explicit. Can you guys help me out here? What's going on with this first one on top? I heard increasing by 2, so plus 2 each time. My handwriting is so awful like this. Plus 2 each time on top. I agree. You could also have seen that the top is just odd numbers. What is it ultimately going to want? What do we want it to be, though? 2n plus 3 will work. Yes, sir. If I plug 1 in, I get 5. If I plug 2 in, I get 7. There we go. So the top was pretty easy there. What about the bottom? The bottom's a little tougher on this one, I think. These are growing faster. You have an idea?
2n squared.
Kyle sees squares. Do you guys see squares? Well, let's think about our square numbers. You should just always keep these in mind. 1, and then the next square number is 4, and then 9, and then 16, and then 25, etc. Do you see Kyle's squares now? 1 times 2 is 2. 4 times 2 is 8. 9 times 2 is 18. 16 times 2 is 32. I think he's got it. 2n squared is that bottom one. So note, as soon as you recognize that it's not multiplying by something, that it's not adding or subtracting by something, you don't have a whole lot of options left. The only other things I told you were squarish things and cubish things. There are, of course, other things, but that'd be too much when we're first starting to learn how to do these, okay? All right, the second sequence I thought was a little easier. I don't know what you guys thought, though. What's going on top? Subtracting by 1, so minus 1 on the top each iteration, or iterate, okay? What about on the bottom? It's adding, isn't it? How much?
2 plus 2 or 2.
You could say each step. I'm just getting you guys used to the vocabulary, yeah? So what is that going to be? Oh, that's a typo. I meant this to be what? 6, and I meant this to be... You guys found my typo. Figuring out that sequence that I had there a second ago, I think would be beyond your abilities or impossible. Probably impossible, actually. Because it changed its pattern in the middle, right? Okay, so what would this be then? It's not just 2n, though. Minus 2? Yeah? No? Yeah, that's it. That's how you get it. Okay, 2n minus 2. How about on top? You guys got the top? We need to minus 1 each time, so minus n should be what you have. 7 minus n will give it to you. There you go. You could, of course, try it. You guys remember, you always want to try it. Let's plug in a sub 5, the fifth term. If we do that, we get 7 minus 5 over 10 minus 2, which is 2/8, which is what this is supposed to say. There we go. Okay, let me erase that here in a second. Get it out of this spot. Let's scoot over. Okay, what'd you guys think on this guy? This one is a little tougher again. Is it alternating? Yes, it is. So you need an alternator. -1 to a power. What power? Let's put in 1 and think about it. If I put 1 in, then -1 to the 1 is -1. Is it supposed to be negative? No, so I'd put in plus or minus 1. Either thing works because that'll make it be like squared, which makes the first thing positive. Okay? So there you go. What else is going on here? Like, what is happening in this problem? It's doubling. I really like what Rachel said, so you could say it's doubling, or you could say it's times -2 each time, and then this negative would accomplish this part, and you'd have to be a little careful about it, but she's right about that. Okay, so doubling, I think that we could just say is times 2n or n? Power or multiply? Power is multiplication. So there's our n. Do you need anything else? Well, if we plug 1 in right now, we're going to get positive 2, not positive 100. And by the way, going back to that problem that was in our homework a second ago, this is what kind of sequence? What type? Not what form, what type? This is an exponential. So you gave me a form. This is an exponential sequence. And exponential sequences usually have what right in the front? They usually have that P sub O thing, which tells you where to start. Where do I start with this guy? Don't I start at 200? So now I think we need to try this. This one's a little bit more complex, so let's try it and figure out what a sub 2 is and see if it's negative 400. So that's going to be negative 1 to the 3 times 2 to the 3 times 200. That's going to be negative 8 times 200. Is that going to be negative 400? I don't think so. So there's a variety of ways you could modify this. In fact, this is not 400, it's what?
Yeah, 2 is what's the second.
Oh, okay. So there's one of my mistakes. You guys caught me. I thought you were talking about here. You guys were talking about here, though, right?
Yeah.
Nice. Let's just go like this, 2. So this is going to be negative 4 times 200, which is negative 800. That's closer, but it's still no cigar. So how could I fix this? Kyle?
Instead of times 200, do times 100.
You could go times 100 and come down here and make this a 1. That's one choice. What would be another choice to make this happen?
And minus 1 now.
You could do what with 800? You could divide it by 2. If you put that down, like on your test, I'd be fine with that. That's the right answer. I mean, that's a form of the right answer. It's not very elegant, is it? It's kind of messy and yucky. But what's another way to fix that? If you're dividing by 2, isn't dividing by 2 equal to 2 to the negative 1 power? So couldn't you go like this? Think about it. That's a better way. So I think Kyle's choice of the 100 or making this exponent be the proper thing, either one of those really gets the job done. If you had a big divided by 2, though, that would also get the job done. It's just pretty ugly. Okay, so there we go. Let's look at something new for today, and we'll continue with this tomorrow. And this is our introduction to series. So we have a little bit of vocabulary here first, and then we'll just work on some series recognition today. So a series is a sum of all the terms of a sequence. That sequence has to be really written most of the time in either a list. We'll look at list series tomorrow. Today, we're going to be looking at series that have the sequence written in explicit notation, like we've been working with. So there's a special Greek letter that's often used here. You guys can see it on those examples below. That Greek letter is named sigma. It looks like this. Sigma means series or sum. Ricky, you need to get off your computer. I don't know why you're on it. So every series or sum has a beginning and an end index, or indices, because this is plural on this guy, right? So they have beginning and ending indices. Those indices, like this one that says 1 to 4, tell you when to start and stop adding individual terms in the sequence. Okay, so let's look at a couple of these. We're just computing series. This is going to be very simple. So this series says start where and stop where, guys. says start at 4, end at 8, and do it with this sequence. So we're going to start by plugging in 4, and we're going to add up each one because it's a sum now. And I've got one more term, right? Oh man, I'm going to shove it in up here. And then I just need to simplify and I'm done. So this is going to be 1 over 3 squared plus 1 over 3 to the third plus 1 over 3 to the fourth. And you guys can see the pattern really easily now, right? 1 over 3 to the fifth and 1 over 3 to the sixth. Of course, that's not simplified very well, so I need to pop this in my calculator. So you could pop this in your calculator. I guess I'll show you guys that today. We'll just go ahead and bring up my calculator. What's it called? We'll type that in. So we've got 1 divided by, what did we have? 3 squared plus 1 divided by 3 cubed plus 1 divided by 3 to the fourth plus 1 divided by 3 to the fifth plus 1 divided by 3 to the sixth, right? So you could put that in your calculator. I'm not looking for this decimal, though. I'm looking for the fractions. There's a couple ways to get that. Depends how strong you want to be on this stuff. I think one way we know how to get this is to go to this math button over here and hit fraction. So there's our answer, 121 729ths. So let's minimize that for a second and stick our answer in here. So we got 121 729ths. There's the answer I'm looking for. You could, of course, get this by hand on this problem. I'm going to show you how. These are all easy, super easy to make a common denominator. What's the highest power? It's 3 to the sixth. So this one is missing 1 3. This one is missing 2 3s. This one is missing 3 3s to make it have that common denominator. This one's missing 4 3s. And then if you come down here and do all that stuff, you're going to get 3 to the fourth plus 3 to the third plus 3 squared plus 3 plus 1 over, what's 3 to the sixth power, you guys? Put it in your calculator. 3 to the sixth power you're going to find is 729. What do you guys think this top part equals? It equals that. So that's how your calculator is doing this business, or maybe that's how it's doing it anyway. Okay, so I encourage you to play around with those kinds of skills that you'll need later on. Let's do another couple series together. So I wanted to look at this one. So this guy, I need to make a little space here. So give me a second to erase this business. So what about over here? Over here we're going to start where? 1 and go till 4. So we're going to go 1 to 4. We're going to go 8 plus first 1 squared. That's the first term. So I'm going to use parentheses to help me out. Then I'm going to add 8 plus 2 squared. You guys can already figure this out, so you should just follow along and see if you can beat me. You got to be able to beat me with this terrible pen I'm using. So that's going to be what? It's going to be 9. 8 and 4 is 12. 8 and 9 is 17. 8 and 16 is 24. Add all these guys up and you know what the series is. So I've got it to be 62. So the sum from 1 to 4 is 62. Over here we had 4 to 8 was 121 729ths. So if you're watching the video now, you want to pause it and try one of those other 2 examples, okay? Why don't you guys try one of them, just one of them. Just pick one and see what you get on that one. We'll do the other one to warm up tomorrow. So the third one should have turned out like this. Now you'll notice that I didn't show my work a lot here. So I kind of just focused on the essentials. You probably need to show your work more than this. When I plug in 2 right there I get negative 1 cubed, right? And when I plug in 2 right there for I get 4 times 2 minus 2. So if you simplify that, negative to odd is negative, 8 minus 2 is 6. There's that first part. So you can see that that's what you're going to need to do on these problems. We'll warm up with this guy tomorrow just to remind ourselves. So the key here is how you read this. What have you just done? You've just figured out, for this sequence right here, you've figured out that the sum from term 2 to term 6 is negative 14. Those terms add up to negative 14. That's the idea of what we're doing here. So before we leave off for today, I want to do 1 or 2 examples of what we're really trying to build up to, which is this, part 3. So this says, practice writing a listed series in the compact notation. So can you guys see what's happening with the individual terms? Forget about the adding for now. What's happening with the individual terms on this one? I think it's pretty simple. What's it doing each time? It's going up by 3. So what's the sequence? This is more practice of what we started today's class with. It's going to be 3, like 3n. Now how do I get the first thing to be 2 from 3n? Minus 1. I could check it by putting in 3. If I put 3 in, then 3 times 3 is 9, minus 1 is 8. Yes! That's the sequence. If you can do the sequence, you can do the series. How many terms did we add up? 1, 2, 3, 4, 5. So my series goes, I called this n, so we're going to call this n. You can name your index anything you want. I had k for an example, right? I had I for an example. K, I, and n are the ones you'll ever see in math. It doesn't matter what you name it. So let's start with 1, because don't we always go on the natural numbers? You can change that, but we're not going to talk about it today. 1, 2, how many? 5. Done. That's it. Let's do one more before we leave off for today. What's going on here? This one's a little bit more difficult, but not too much. I see powers of 5. You guys see the powers of 5 that Miss Sierra is talking about? I love it. So we're going to have on the bottom, so should we just go 1? Powers of 5, like 5 to the n? Yeah. Because then if we put 1 in, we'll get a 5th. We've got a couple more things to worry about, though, here. We got plus, minus, plus, minus. How do I do that again? Don't I need this in front or back? Now you guys tell me n or n plus 1. If you're not sure, just guess. I heard n plus 1, so I'm going to go with that. I haven't even thought about it yet. If I plug in 1 now, I get squared. Squared is positive. Is it supposed to start positive? Yeah. If I plug in 2, I get cubed. Cubed is negative. Is the next one supposed to be negative? Yeah, it worked. If you're not sure, just try one, guess, and check it. I think that's it. The only thing I need to do is fix my indices. My indices here should go n equals 1 to what? This is an infinite series. Now this year we aren't going to work much with infinite series. That's more of a calculus topic. We certainly could, but I'm going to skip most of the material on infinite series. But I'm just showing you that you could think about these series adding up forever. So an interesting side note is, if you add up some series forever, does that mean you just get infinitely big or infinitely small? Like, is this always going to go to infinity as your answer, or maybe it'll get really tiny and be negative infinity? The answer is some infinite series settle down. And this is part of the magic of modern technology. So if you're watching the video at this point, I think you want to pause and try 2 problems. So this is where my class is going to pick up on the second day this year, and we're going to work on figuring out this series, finding the sum of finding the sum of 3 terms from 5 to 7 for this sequence and adding those up. And then we're going to go down here and finish up this problem and try to express this little summation or series in compact sigma notation. So pause the video and try those out now, and then you can come back and check your answers. So let's see what we get on this guy. So let me switch to blue. So this guy, we're just going to add up, I think, 3 terms, 5, 6, and 7. So first we're going to have negative, I'll just go black, negative 1 to the 5th times, I'm not even going to write that, times 5 squared over 3 to the 5th power plus negative 1 to the 6th times 6 squared over 3 to the 6th power plus negative 1 to the 7th, and I'll stop there because I just want to go up to 7 like it says here in the summation notation. So 7 squared, and that's going to be over 3 to the 7th power. So now I just want to simplify this down. Negative to odd is of course negatives, that's negative 25. 3 to the 5th you might not remember from your power tables. Let's see, 3, 9, 27, 81, 243 is, I think. Yeah, we'll check with our calculator in a second. Negative to even is of course positive. 36 is on top, and 243 times another 3 is going to be, I think, 729. Negative to odd is negative. That's going to be 49 on top. And then 3 to the 7th, I don't know if I know what 729 times 3 is. So we're going to figure out what that is. So let's figure out what this is. Let's go to our calculator here. Let me pull up my TI-84. So here's my TI-84. Make it a little bit smaller so we can see what we're doing. A little smaller. Oh, does it not want to go any smaller? It doesn't. We can see what we're doing there though. So what do we need? Negative 25. So I'm going to go negative 25 divided by 243. And I don't need to wrap this fraction in parentheses because then I'm just adding on the next fraction separately. Remember, if you're ever confused about whether you need parentheses or not, if in doubt, use parentheses around every numerator and denominator. And then we've got minus 49. And see, the denominator down here has 3 times 729. So I'm going to do that whole thing. So let's see what that is. So now you don't want just this decimal, remember. I want you to rationalize it. So you could use a common denominator if you want to do it by hand, or otherwise I need you to press math, fraction, and have it reduce that for you. So there's what we're going to have on this one. We're going to have negative 166 over 2187. So there you go. That's what the sum of from term 5 to term 7 is going to be, that number. If I can write. Okay, let's look at this other warm-up problem that you should have looked at. So now we're going to try to recognize the sequence first. So what's happening with the sequence here? I think this one you can definitely do quite a few ways. You should recognize your square numbers on the bottom. So we have our square numbers on the bottom. So I'm going to say one way to write this, I'll do it in black first, is going to be, well, I want to leave some space for my sigma, right? Because we're going to get this in there in a second. But on the bottom, just for the sequence part of it, I've got the square numbers. So I've got like n squared. So I think we could go to square numbers. And then we've got the thing that squares into those numbers on the top, right? Like 2 squared is 4, 3 squared is 9, 4 squared is 16, and so forth. So if I call the bottom n squared, then I better call the top n. If I do it this way, though, I'm really not starting at 1. What am I starting at? Ask yourself. I think you're starting at 2 then, because then we're at 2 over 2 squared is 4. That's the way we're going to go. So then how many terms do we have? We have 1, 2, 3, 4, 5, 6. So this is 2 to 6. So that'd be one answer right there. You can, of course, simplify that, I hope you realize, to the series from 2 to the 6. N over n squared simplifies to just 1 over n. So I think that'd be one form of the answer, because of course, remember, these could simplify to 1/2 plus 1/3 Let me make you have a nice 3 here, and that's 1/4 plus dot dot dot, and then we're stopping at 1/7 right here, right? So you can see that, why didn't I give you that to begin with? Well, because I wanted you to think about it a little more interesting problem. There'd be another way to do this too, though, I think. So another thing that this is going to be equivalent to is, I think we could take the summation. What if we wanted to start at 1 instead of at 2 and go the first 5 terms, right? Because that's what we got. 1, 2, 3, 4, 5, 6. Oh, there's 6 terms. This is the first 6 terms. So really, I have a mistake up here, right? This is not supposed to be 6. This is supposed to be 7. So let's fix that up. This should have been term 2 to term 7. And I think that makes sense then. So I could also go 1 to 6, but I'm going to have to change things a little bit. If I go 1 to 6, this isn't just n squared down here anymore. Then I've got to say it's n plus 1, all quantity squared. So now if I put 1 in, I get 2 squared, which is 4. There we go. So then on the top, then I'd have not just n, but n plus 1. And you notice this one reduces just like the other version to become n equals 1 to 6, and that's going to be 1 over n plus 1. So you can see these are 2 different versions of the exact same thing. I bet you probably could have figured out another one, so maybe you did. Let's look at the last thing in this lesson. So I wanted to just tell a brief little story here. I didn't have a picture prepared. But this story is about Carl Friedrich Gauss. Carl Friedrich Gauss is one of the most prolific mathematicians of the late 19th century. So that's the late 1800s. So he's still pretty old, but not too long ago. Your great-grandparents' generation or so, something like that. So Carl Friedrich Gauss was a student in Germany, I think North Germany somewhere, but don't quote me on that one. And there's this really famous story about Gauss when he was in like 3rd grade or something like that. So Gauss was in like 3rd grade, and he was kind of being a little bit of a rascal. He was causing trouble in class, and so his teacher, being a strict disciplinarian, said, "Okay, Gauss, let's keep this kid busy. He's always getting his work done way too soon. Can you add up the numbers 1 to 100 for me, Gauss?" And she was thinking, "Oh, this will take him a long time." And so Gauss, he took 30 seconds, maybe even less. I've heard the story go. He took about 10 seconds, and he said, "The answer is 5,050. And so the little 3rd grader tells her this answer, and the teacher's not sure, and so she goes and checks it out later on, thinking that he's just messing around, and she figures out that yeah, it actually is. So how did Gauss do that in about 10 or 30 seconds? So I think the answer is this. He used this pairing method. So let's start thinking about adding up the numbers from 1 to 100, that series. That finite series. I mean, it seems like it's easy, but if you start adding them up without a calculator, it becomes tough in no time. So I don't think that Gauss really started adding these up like the teacher expected. What he did is he paired some things up. First he said, well, what if I take the first number she wanted and add it to the last number? And then what if I take 2 and add it to the one second to last? And 3 and add that to the one second to last? And add 4 to the next one? And so forth, and pair things up like this, and then add these guys up. So Gauss figured out, 100 plus 1 is 101, and 2 plus 99, that's also 101. 3 plus 98, that's also 101. So these are all turning out to be 101. So now the only thing you've got to do is you've got to figure out, I really just have 101, so this problem is equal to 101 times what? I think it's 101 times 50, which Gauss figured was just 50 times 100, which is easy to do in your head if you're a bright 3rd grader, plus 50 times 1. 50 times 100 is, of course, 5,000. And 50 times 1 is, of course, 50. So that's how Gauss came up with 5,050 so quickly. So he was a bright 3rd grader, but I think you'll find that quite a few 3rd graders could do this if you prepared them the right way. I don't know if Gauss was prepared the right way or not. But what I wanted to show you is this is a shortcut formula. This is one of the examples of, I don't want to just call this summation formulas like the book does. These are shortcut formulas, shortcuts, okay? And we do kind of need to memorize these. So which one of these is the formula that Gauss came up with? I think this one is the one that we just worked with. The sum of the first k numbers from 1, the sum of the first n numbers, where you're just going plug 1 in, and then take 2 and plug it in, and then take 3, and you can see that's exactly what we just did here. So where does this match what Gauss kind of figured out with his little pairing method? This is what you need to memorize. This thing is uber super important. How's this match? Well, if you go from the sum of k equals 1 to 100, like his teacher said, and you follow this formula, then that's going to be, you put this number here, so that's going to be 100 times 101 all over 2. Where is this up here? Well, you can see very clearly the 101 is right there, and 50 is 100 divided by 2. So really this is Gauss discovering a shortcut formula that's oh so important as a young man. So we need to definitely have that one memorized. And for my quizzes, at least temporarily, you need to try to memorize these other ones as well. This one is super easy. I don't think it requires memorization. What if you don't have a variable? What if it's just a constant? In other words, what if you have the series of like 7 from 1 to 5, for instance? Well, that's just 7 plus 7 plus 7 plus 7 plus 7. Well, another way to think about that is 7 times 5. So, of course, the shortcut formula says if you've got any constant c, just multiply by this number right here. Oh, I've got a cat. Cat problems. Hold on. Oh my gosh, cat. Okay. And you'll have the summation of that constant. So that's that one. We could have come up with another pairing method or something clever like Gauss did to figure out the sum of the first or first n square numbers. That'd be, of course, 1 plus 4 plus 9 plus 16, etc. This guy is how you do it for the first square numbers, okay? So let's see an example of where this is useful. If we were going to try to sum up the first 400 terms in this sequence, that'd be pretty difficult to do the way we did a second ago, so we really need these shortcuts. Let me get all my mess out of the way. And we'll look at our shortcuts, and we'll make some decisions, and then we'll just feed it to our calculator and have it do it for us. I really need you to use these shortcut formulas. There are, of course, ways to do this on your calculator without them, but the power of this is learning the shortcuts. That's really what we want to focus on. So the first idea here is I want to distribute this sum to all 3 terms that I have here. So I'm going to have the sum of 8, I'm going to have plus the sum of 6k, and then I'm going to have minus the sum of k squared. I want to put my indices on here, so this is k equals 1 to 400. Here we've got 1 to 400, and here we've got 1 to 400. And also, I'm going to just, something you can do with sums is you can factor out any constant multiples. So I'm going to take this 6 and factor it out in front, like so. And now I'm going to use my shortcut formulas. Remember, this says 8 plus 8 plus 8 400 times. So that's 8 times 400, or 408s. That's this formula right here. The next one, you can see, if you look at it, it matches the notation real clearly with this guy. I've got 6, okay, 6 times the sum of k, which is 1 plus 2 plus 3, just like Gauss. This is Gauss's formula. Let's remember it is Gauss's formula. So how's that going to go? Well, I'm going to go 6, and then I'm going to use my formula here. So I'm going to put this top number first, so that's 400. Then I'm going to go 400 plus 1, and then I'm going to go over 2. And that's it. Then we've got the sum of k squared, which is, of course, this guy, so we'll use this formula. So now we're going to take that n and plug it in the spots. So we're going to have 400, because that's n for us, 400 plus 1, and then right in here we're going to have 2 times 400 plus 1, which is, of course, 801. And that's all going to be over 6. We just have to feed this to our calculator and we'll have it. So let's pull up our calculator and finish this last example for today. So let's see, where did my calculator go? Okay, here it is. Let's clear it out for us. Okay, can we get this up here? Nice. Okay, so let's go 8 times 400. I'm going to add 6. And you know what? You can do some nice reductions here. It might be nice to go down here and like reduce that and say 6 over 2. 6 divided by 2 is 3. So I'm going to do that and say 3 times 400 times 401. And I don't even have to use all my parentheses if I think about what I'm doing with order of operations. So over here I don't see anything that reduces real nice. The 6 doesn't go in nicely, at least to any of these numbers, so I'm just going to go plus. I'll just put a big fraction in safely with alpha y equals. Okay, so we've got 400 times 401 times 801, and then I've got 6 on the bottom. All right, adding those all together, bam, there's our sum. It would have taken us a long time to do this. So just make sure that you're doing this. So what is that? 218978. 218978, and I think there were 2 zeros on the end, so what is this sum up to? This sum from 1 to 400 of this sequence will add up to 21,897,800 at the end of the day. Whew, that's really seems like a lot of work, but man, these shortcut formulas that I'm cleaning up right now, these guys really make it happen. So I hope you value the power of these shortcut formulas, memorize them, they're your best friends as soon as possible. Just make sure you don't cut off a 1 like that. Alright, you should be set for everything in 12.1 and 12.2. I will see you next time.